So we're going to continue our discussion that we started last time of what hardware support is actually required for implementing an operating system. If you have a hardware platform that doesn't have all these things, then you're going to have a pretty weak operating system. And this is kind of why we're going to talk about MS-DOS, and I'm going to probably reminisce a little bit about all the naughty things we could do under MS-DOS, because it was fun. But the reason why MS-DOS sucked so much in that way is because the hardware support just wasn't there for creating a good operating system. And it wasn't until about the 286 or the 386 that we started being able to create real operating systems on that processor family. Other processors supported all of these things well before the x86 family of processors, so those operating systems didn't suck. But we kind of had some limitations because of what the hardware supported. So we had these components that we talked about, and we pretty much covered all of them. And we talked about how applications are not allowed to talk to the operating system directly. That was one of the characteristics of DOS, is that you could talk directly to the components of the operating system. You could modify them. You could create TSRs. You had all kinds of things you could do. So, but modern operating systems, we don't allow direct access. And of course, the code and the data that the OS manages are in kernel space and can only be executed in kernel mode. So we had that constraint. And the application code and data is in user space and it can be executed in user mode or kernel mode. So the question is, how does the application actually get into the OS? And we talk about this in CS124, so we don't have to spend too much time talking about it. But typically what happens is you execute an instruction that allows you to trap into the kernel. And almost always this is going to be some kind of software generated interrupt that allows you to transfer from user mode into kernel mode so that you can now start executing kernel code and access kernel space data. So those are the details of how we get from the application into the kernel. And I mentioned faults here just because we'll go through all of that again just as a review. But remember, there's different kinds of interrupts. There's ones generated by hardware. There's ones generated by software, and different circumstances. They have different implementation details and different behaviors in the CPU. Remember that faults always go back to the instruction that generated the fault, because we may be able to retry it. Traps, on the other hand, and hardware interrupts go to the next instruction. So let's see, the OS initialization, the kernel sets up basically handlers for various kinds of interrupts, both hardware interrupts and software interrupts, so that when an application decides it needs to get into the kernel, it invokes the trap instruction, and then that causes the trap handler to be invoked. And the processor is going from one mode to another mode almost always. There's very few situations where a kernel would trap into itself. It's like, why would it do that? It can just call the handling code directly, so there's no real reason to. So like it says here, the processor can change into kernel mode. There's two benefits from doing this. One you may not think of so much, but it is nice to have a level of indirection between the application code that needs to invoke some operation and the operation being performed, because it may be that over time, as the OS is upgraded and code is added, code is removed, the addresses of these handlers are going to move. And so it doesn't make sense to have an address coded into an application. We need something indirect. So again, remember, indirection is our friend almost always. If we can introduce indirection, it gives us more power and capability. So having a trap handler, and of course, again, you probably all remember, int80 is the Linux and OS 10 trap handler. And on Windows, they have like 2E, hex 2E, or 25, I can't remember. There's a couple of different trap handlers used by various operating systems. And so it's like everybody knows. That's how you get into the kernel. The kernel can structure the code however it wants. The other one is the more obvious benefit, which is that the operating system now has a controlled entry point, a single controlled entry point that can be hardened, and the operating system can make sure that there's no bugs in this, so that the application's requests and the arguments can always be evaluated. And we'll talk about this when we get to system calls. When I do a read operation, then I'm passing the kernel a pointer, and I'm asking the kernel to write data from a file into that pointer, the memory pointed to by that pointer. I may not be able to access it, but the kernel can access anything. So what if I give it a pointer to something in kernel space? Now I want the kernel to shoot itself in the head. So the kernel has to be clever, and it has to say, okay, thank you for this pointer. I'm going to verify that this is not a pointer that will cause harm. So, for example, it makes sure that it's in the address space of the user application. It's not in kernel space. That's one simple check that you'll have to implement for your system call implementation when we get to that point in Pintos. Simple example. Okay, so IA32 uses int. Let's kind of rush through this kind of stuff because who cares? We already talked about a lot of this stuff in CS124. But the different operating modes have different stacks on IA32, and this is not an uncommon approach. It basically allows the kernel to be insulated from the application. If you have an application that's behaving really badly, then you don't even use the application stack. You can use the kernel stack. And this interaction between kernel stacks and application stacks is actually pretty interesting, and we'll talk about it especially when we talk about how signals are delivered to applications. So arguments are typically passed in registers, and so you say what operation you want to perform. You also say here are the arguments. That obviously constrains the number of arguments you can have because you have a limited number of registers. And we had this example where I want to retrieve the process ID of the current process. And so I stick the value 20 into EAX. I invoke hexadecimal interrupt 80 or 128. And when the interrupt handler returns, the operating system has placed into EAX the process ID of the calling process. Okay? So that's a really simple example. We don't like to do it this way. We like to actually use the syscall wrappers that are given to us, but it's nice to understand exactly what's going on under the hood. Okay, let's see. Are there any questions about this at all? Any basic questions? So we're going to start diving into how it all works. All right. So IA32 has this big table, tabular data structure called the interrupt descriptor table, which basically says this is the handler to invoke for each interrupt. And of course, since there's 256 interrupts, this table has 256 entries. And from 5X, you may be familiar with the interrupt vector table where we have 4-byte entries, but in protected mode, we actually have 8-byte entries because they have to have an address and they also have to have details about whether or not you're allowed to invoke this handler from a particular protection level, what protection level should you enter when you go into it, and so forth. There's a few other details that could be specified there as well. Okay? So you have some interesting details that have to be specified. So the interrupt descriptor table has larger entries. But they're all the same size, and so when you say int n, the processor does very simple computation, like shifts it at, left by 2 bits, 3 bits, something like that, some number of bits. And then it looks up the entry in the interrupt descriptor table and does a simple check. If the caller is at some protection level, then it transfers to the interrupt handler. Otherwise, it would probably generate some kind of fault that the interrupt is not allowed. Okay. Of course, most of the time, the way operating systems implement traps is they'll say you have to be at you can be at the lowest protection level, and we go into a high protection level to get into the trap handler. And then the trap handler can do its thing. When the handler is finished, it does the IRET, and so that does the sequence of steps, basically getting back to the caller's privilege level. And the way that we set up this interrupt descriptor table is to use the LIDT instruction, and then that basically allows you to say this is where the interrupt descriptor table starts. So that's basically what we do there. Okay. Now, also, booting. We haven't talked about booting yet. We will a lot next week because it will be important for your second assignment. But it's really gross and it's grungy, and I am apologizing right now, but I'm sorry, software has to run on hardware. So basically, when the IA32 processor starts, it starts in kernel mode. You're in ring 0 because you're in the operating system code. You need to set up the hardware, and so you need to be able to do all of these kinds of things. So basically, that's how you can go ahead and configure all of these things, and then you can later switch into user mode once the operating system is ready to start executing user applications. Okay, so that's basically the general idea of how we dispatch to these things. You'll see a very specific example of this, I'm pretty sure, in the second assignment, because I want you to be able to handle keyboard key presses. And the way to do that, obviously, is to set up a keyboard handler. So we'll explore that. Okay, exceptional control flow. So there's a lot of other operating system facilities that depend on exceptional control flow. Traps are the ones that we talked about, and of course then you have hardware interrupts. Okay, so we just generally call these interrupts. And basically you have a lot of long-running operations. I want to wait for network data to arrive, or I want to be informed when network data has arrived. I want to be informed when a disk performs some operation. Let me know that data is available, something like that. Or even timers, and we'll talk about timers a lot in a moment. Okay, faults, usually unintentional, but it is the mechanism by which we implement virtual memory and memory protections. So like I say, here's a potentially recoverable error. And so the fault handler tries to handle the fault and then goes back to the faulting instruction to try to execute it again. And if it succeeds, then yay. And if not, so another thing that you'll notice about this class is that there's a whole bunch of new ways to have infinite loops. And one of the ways is to have a faulting instruction where the fault handler doesn't resolve it, and then you go back and fault again, and I think you actually run into this in the virtual memory lab like right away. You run into faulting instructions. And you might have a loop that way. And then aborts are the non-recoverable hardware errors. Okay? So these are when I run into some situation and I do not trust that I can actually continue computing. These tend to be the kinds of things you see for aborts. IA32 does have one. It's called machine check. And I can't remember exactly what causes it to occur, but it basically causes your system to halt. Okay? Let's see. Now, other ones that will be more relevant to you as we get into assignments 3 through 6 are ones that are, they typically indicate operating system bugs. So you have a double fault abort. And the scenario basically goes like this. You have an interrupt that occurs, and that's all fine. You know, this is all normal operation. And so the CPU looks up in the interrupt descriptor table, what handler do I want to invoke to execute or to handle this interrupt? And so the CPU tries to invoke the handler, and in the process of invoking it, we get another issue, typically as a fault. So let's say that the handler is not in the address space, or it's not allowed to be executed because there's a protection level issue. You could have a number of other things that could occur as well. But we basically have a fault in the process of dispatching an interrupt. So that's a double fault. Okay. Now here's another one that causes a double fault. And this one, again, is one that you will probably see at some point. So you have a user program that triggers a page fault, and then in dispatching the page fault handler generates a page fault. Okay. Because if you think about it, what is supposed to be used to resolve the page fault? The page fault handler. So if invoking the page fault handler generates a page fault, you're done. Game over. Okay? So these, you can see, are generally caused by operating system bugs. Now you can register a double fault handler, which is kind of nice. If I remember correctly, I can't remember exactly how this is all done in Pintos, but we'll remember very quickly when we get into those assignments. But I believe that Pintos has something set up so that you can actually like trigger GDB or something like that when you get into a double fault or a triple fault situation, so that you can say, okay, yeah, things are going bad fast, so let's get into the debugger and see exactly what's going on. So you can register a double fault handler if you wish. Although generally what this would do is try to recover the operating system to a point where it can continue executing. So you try to limp back to life if you possibly can. Linux has a really interesting mechanism for trying to deal with kernel bugs, which we'll talk about when we get into system calls. So basically, the amount of times that you see a kernel panic should be relatively infrequent because it can actually recover from a significant number of issues. Okay. Now, let's say that it tries to invoke the double fault handler, and that also generates a fault. Okay. Then you get a triple fault. And don't worry, we don't have quadruple faults and quintuple faults and so forth. Basically, the CPU gives up when we see a triple fault. Okay. What happens is basically either the system resets itself, it basically does a hardware reset, or it waits for a user to do a hardware reset, or in rare situations, like if you're on a multi-core system, you can have one core try to reset another core. Because obviously all of this is occurring in, it's an interaction between software and hardware, but it's an execution path. So if you have multiple cores, you might have one core that's flipping out and another core can try to reset. Okay? So I just want to point this out when we talk about interrupts, because it's not uncommon to see these in CS124. And again, another kind of infinite loop. You have code that triple faults. You see your system reboot. Then it tries to stand up, and it triple faults again, and it reboots again. So if you ever see your operating system just rebooting over and over and over again, have fun. That's the issue there. Okay? Any questions? All right. So, hardware interrupts. So certain kinds of multitasking, we require hardware interrupts. We also require another facility that we're going to talk about now. So simple operating systems will use cooperative multitasking. It's kind of a very easy way to stand up a multitasking system is to have cooperative multitasking. You rely on processes to either voluntarily release the CPU or do any long-running operation, because typically the long-running operation also informally relinquishes the CPU. So, for example, if you ever, I don't know, again, you guys are getting so young. I started teaching when I was 29, and so this kind of stuff happened all the time. But now that I'm 40, it's like probably none of you have written Windows 95 code or pre-Windows 95 code. Definitely, I would guess. Nobody's written like Windows 3.1, Windows 4 code. So, but you're talking now, or pre-OS 10 code as well. You're talking about operating systems that actually implemented cooperative multitasking. And most of the time you didn't actually think about it. But if you wrote a program that did I/O, then you were implicitly cooperating, because when you would do an I/O operation, the operating system would make you release the processor. Okay? But if you just did a compute-intensive thing, you could cause the whole operating system to halt or seize up. Okay, so but basically, the processes were required to be good citizens in these kinds of systems. And of course, this is a bad assumption to make. It's very easy to write a broken program, it turns out. Or it's easy to write a broken driver. And that was frequently what would happen is you would have drivers that misbehaved. And so when the program called into a driver, it would cause the operating system to fail. Nonetheless, you had a number of operating systems that basically only did cooperative multitasking for a surprisingly long time. So all Windows operating systems up to Windows 95 actually were cooperative. And Mac OS before OS 10 was actually cooperative. It did cooperative multitasking. And then there were a lot of other older operating systems that did cooperative multitasking. Interestingly, the exception, Unix variants, remember that Unix was designed for mainframe computers and mini computers and things like that. So we're talking about large systems where we couldn't keep them maxed out unless we supported some kind of multitasking. So Unix variants pretty much supported multitasking and preemptive multitasking all the way along. It was only these desktop systems where you had a single user and there wasn't really heavy multitasking requirements that you could rely on cooperative multitasking. So, of course, the solution to badly behaved programs in the context of cooperative multitasking is to preempt them sometimes. And the way that we preempt them, you drive the preemption by introducing a hardware timer. So the OS configures the timer. It says, I want you to get back to me in, let's say, 10 milliseconds. And then you go ahead and turn over execution. You turn over the processor resource to the program. And the program executes. And if the program doesn't do anything that requires kernel intervention, then the timer goes off and it can intervene and switch to another process. So this allows us to do preemption now. Okay. Let's see. If you want to do this kind of thing, you have to have a timer that is only configurable in protected mode. Because if you don't, then an application could just get on there and say, hey, I'd like the timer for like ever, never trigger. And then the program gets to have the CPU forever. So the operating system has to have a way of saying the timer can only be configured by me, and then you have an operating system that's pretty bulletproof at that point. Okay? Let's see. Yeah, and so all of our operating systems now that we use have preemption. Thankfully, people have gotten a clue and implemented things in a clever way. And as I said before, all the Unix variants basically had preemption from day one, so that wasn't something they needed to add. Okay? So, any questions so far? Just to talk a little bit about how this is implemented, there's a particular component on your Intel PC system or x86-based system called the Advanced Programmable Interrupt Controller, or APIC. Okay? People frequently call it just the APIC. And basically, it allows you to configure your interrupt handling in a lot of different contexts. It's a very powerful component of your system. There's a lot of different sources that it can receive interrupts from, and so the APIC has, as well, several different components. You have the local APIC, which is sort of close to the processor proper, or the core itself, and that'll handle things like interrupts that can occur, hardware interrupts, and then also local I/O operations that may occur. And like I say, timer-generated interrupts, thermal sensor interrupts. Hey, your processor is 980 degrees. You should probably stop it or slow down the CPU clock, things like that. A few other details as well can be configured on the local APIC. And so I'll talk a little bit more about that in the future. There's also an I/O APIC, and that basically lives on the motherboard and allows you to configure things like disks and keyboards and so forth, so that those things can be delivered to the processor as well. Okay, so you may have noticed, like on Bootstrap, especially if you don't use a Mac, if you use a PC and you happen to be from the BIOS days as opposed to the UEFI days, and we'll talk about what those things are next week. But you'll sometimes see interrupts assigned to devices. You might see that in the text right at the beginning of boot up, and that's where the I/O APIC is being configured so that the operating system can say, okay, this device is mapped through this interrupt into the processor, so the operating system can know what interrupt that certain things will occur on. Okay. Other details, like I say here, different devices can have prioritized interrupts, so that if two of them occur at the same time, which one is delivered? Or I should say which one is delivered first. So those kinds of things can be set up. All right, so yeah, the I/O APIC usually lives on the motherboard. Now, if you have a multi-core system, then it gets a little bit more interesting, and this is honestly one of the more fascinating aspects of multi-core operating system development, is figuring out how to get all the processors to play well together. If the local APIC no longer gets interrupts that are I/O interrupts, it now only gets APIC interrupts, and it starts getting its I/O interrupts from the I/O APIC. And then all the processors share an APIC bus that allows these components to communicate with each other. Okay. Why might that be? Well, you have a couple choices. You can either round-robin interrupt delivery so that no processor is stuck always being interrupted in what it's doing all the time, and that way you kind of spread out the load. It kind of is a good way of reducing interrupt latency, or the average interrupt latency, by spreading out interrupts. But there's an interesting issue that if you have all the processors handling interrupts, then the caches fill up with the interrupt handler code, and it takes away from application code and so forth. So sometimes people like to put all the interrupt handling on one processor. So there's different ways that the operating system can configure it, and so that's one of the example details of what the APIC, how the APIC can be configured. Okay, I want to set up where interrupts are delivered. Do I want it to be round robin? Do I always want it to be a specific processor, and so forth? Processors can also use this APIC bus to communicate with each other. So every local APIC has an ID. You can actually use, I can't remember if it's a CPU ID instruction or CPU info instruction, or if there's somewhere else that you get this information from. It's been, I think, a year or two since I looked at this. But you can look at the APIC IDs, you can retrieve them in software, and then you can use that to cause an interrupt on a specific core. So like it says here, IPI, those are inter-processor interrupts. And so you can say, hey, everybody, wake up. Or you can say, hey, everybody else, wake up. Or you can say, hey, so-and-so, I need your attention. And so imagine that you have a program that's running out of control, and it's running on a different core, and you'd like to kill it. Well, then your core can signal the other core, cause the operating system to start running on that core, and then it can step in and interrupt the or kill the process. So there's various mechanisms that you can interrupt, that you can use for causing these cores to communicate or collaborate with each other to carry out OS facilities. Okay, any questions? All right, so that's that. Yeah, hardware interrupts also for long-running I/O operations. So again, this is just covering how all we use these interrupts, this interrupt facility. We had this example from CS124, and it's going to be pretty important to you in your command shells because you'll actually have to use read and you'll have to use write. Or maybe you won't directly, but at least you can look at the utility programs that I provided and see how they are used. It's really straightforward. You just read a bunch of data into a byte buffer or whatever, write it back out. So I want to perform a disk operation that's slow, so the operating system sets this up, tells the disk controller, interrupt me when it's finished, and then it can put that process in a queue saying this person's blocked on this disk, and then it can switch to another process. Okay. So you can see that interrupts are very important for being able to maximize the utilization of the processor. Okay. So these are the hardware requirements of modern operating systems. So we can just sort of review this real quickly. At least dual mode execution. So I have to have user mode and kernel mode. I have to have some facility for specifying process address spaces and process isolation. Okay, so I have, and also like I say here, protection from the operating system, between operating system and applications. I have to have the ability to trap into the kernel. If I have isolation and protection set up, then I have to have a way of getting in. So that's the trap mechanism. I have to have software interrupts and hardware interrupts so that I can implement preemption. And I can also have devices interrupt me when they're ready so that I can have an efficient operating system. And then the hardware timer facility allows me to implement preemption as well. Okay? These are all the things that are required for modern operating systems. Any questions? Okay, so that's that. Yeah, and we're going to dive into a lot of this stuff. Obviously we'll talk about dual mode execution when we get into system calls. We'll talk about, you'll run into the hardware timer right away when we get into Pintos because you'll have to add some facilities for kernel threads and so forth. And thankfully you don't have to talk to devices directly in Pintos, but you will have to think about virtual memory management. So that'll be another place where you see a lot of this stuff. So we'll talk about these facilities as we need them. So the next thing that I want to talk about is, and we'll take a couple of lectures to cover this, is basically the common structural patterns for operating system implementation, or OS architecture. So the number one thing that you'll notice is this, it's called separation of policy and mechanism. Okay. Again, just like anything, we have a separation of concerns, but specifically in operating systems, you frequently have a choice of what needs to be done and how do you actually do it? And you do not want to combine those things in the same place because it's just ugly, and it turns out that one of these things changes all the time and the other one doesn't change very often. So like I say, your policy says what needs to be done, and the examples here are virtual memory paging and process scheduling, really good examples of things that have different policies, many different policies that you can choose. And then the mechanism says, how do I actually do that thing? So virtual memory pages. I need to evict page so-and-so. Okay, how do I actually save it? What do I do to the page table? Those kinds of questions. Okay. When I have a process that should be run next, okay, so it picks which process should run next. Now I need to save the current process's context. I need to do the context switch, and I need to restore the next process's context. That's mechanism. How do I actually implement that changeover? The way that these operating systems work is that almost always the mechanisms rarely change at all. You obviously see differences from OS to OS, But within an OS, the mechanisms change very little. And with a given set of hardware, obviously it's going to change very little as well. So the mechanisms basically don't change very much. But the policies may change so often that they are even part of the operating system configuration. Okay? How many people have Android devices? Yeah, I have an iPhone now. I used to have an Android phone. How many have heard of the governor on Android? Yeah, a few of you. So the governor is a component that chooses what clock speed should your phone run at. And obviously, you want a governor to decide that, because if you always ran it at the maximum speed, your battery would last probably like 40 minutes, and then you'd be sad. And if it always ran at the slowest speed, then your phone would be unresponsive and you'd be sad. So the governor chooses how to control the CPU clock. And there's many governors you can install on Android. If you have your phone rooted or you have root access on it, you can easily configure that. How you actually control the CPU speed itself is obviously mechanism. So that's outside of the governor. The governor specifies the policy. Okay, so operating systems can follow various structural patterns. There is a structural pattern which is not a structural pattern, which is the simple structure, which kind of means big ball of mud. Okay? So there's no clean division into modules. Every part of the OS can access every other part. It's really fun. It's, you know, either Wild West or Steel Cage Deathmatch, pick your analogy. And basically everything can also access the computer hardware. And it usually happens when OS development happens incrementally without careful upfront design. Okay? And there's quite a few example OSs which fit this design pattern, actually. So problems are pretty obvious. You have a lot of issues related to bugs. An OS bug can make it really easy to break everything. Application bugs can bring down the operating system. And I'm serious. The example that we're going to talk about for the simple structure pattern is MS-DOS. And it was very easy for an application to bring down the entire computer because the operating system was very light and very limited in its capabilities. Okay? So, and like I say here also, when you have something that's not well structured or well architected, it becomes very easy to extend the OS's functionality at some point. So, MS-DOS, there's a part of the reason why MS-DOS is so I have to be careful how I say that. I don't want to just bash on it because I actually really enjoyed using it when I was a kid. But part of the reason why MS-DOS was so limited is because of the processors that it ran on were also limited. There was no protected mode execution. And basically, this is how it worked. You had the computer hardware, which you could use ROM BIOS calls to get into the computer hardware. I want to change to we didn't even have VGA necessarily back then. So you would have, like, I want to do 4-bit, CGA color. You had 4 colors. It was great. I want to have device drivers. They may call into the BIOS. They may access hardware directly. They would somehow be installed in memory. Then you had resident system programs that could access any of these layers, or they could talk to the hardware directly. And then applications, which could talk to any of the layers or the hardware directly. It was fun. You could do anything you wanted to, which is also why it was scary. Okay? So you had computer games that would talk directly to the computer hardware and put the graphics cards into graphics modes you've probably never even heard of. Okay? There was a thing called Mode X, which was very popular for early computer games. The computer video hardware was set up to be very optimized, and you could do some really clever stuff, and it was pretty neat. No 3D acceleration at all. You could also have libraries, like extended memory libraries. It was really common that you needed to get some library to allow you to access the full megabyte of memory or something like that, because usually you'd start out with 640 kilobytes, and then you had to do special things to get to the full megabyte, and then if you wanted multiple megabytes of memory, forget about it. You had to do some really crazy stuff to get that stuff. Also, malicious programs, which I certainly had a lot of fun exploring many different kinds of malicious programs, because I had a real interest in computer viruses back then. And there were certain kinds of viruses that would be able to basically, the interrupt vector table is in the first part of memory, and anybody could write to it. And so you could just capture all interrupts coming through, because int21 was the DOS interrupt, or you could what's the word I'm looking for? Intercept. You could intercept any of the BIOS interrupts as well, and you could basically change the way they behaved. And so a lot of times what these stealth viruses would do is they would cut out a little bit of memory at the top of the address space, the 640 kilobytes. They'd put themselves there. They would redirect DOS interrupts into their code so that they could handle them, and then they would delegate out to DOS when they needed to, or delegate out to BIOS. And then when you had calls that would say, how much memory is available? Or, I want to open this file. Well, they would all go through the stealth virus, so they could just pretend like everything was exactly the way it was before. It was really clever. Really dastardly, too. So it was quite interesting. This was part of what got me interested in this low-level system stuff in the first place. All the things that you see stealth viruses do, which is not possible now, by the way, given how the hardware works. Okay, now Unix, a little bit better than DOS. They actually thought more carefully about this stuff, and I think, again, it was because they had systems that were used by a lot of people concurrently. And so you did have this division between applications and the kernel, and you did have system calls and so forth. The kernel itself, I have all these pretty boxes below the system calls, and that wasn't the way it was initially. It was all kind of, again, simple. Everything was together. But then over time, they developed more structure, at least from a software engineering standpoint, but it was still all in the kernel. It was all still in kernel mode. And so this approach is called a monolithic kernel, because the kernel contains a lot of things. Okay? And it is still possible, because if you have all of this code running in kernel mode, it's really easy to have one bad bit of code compromise the entire operating system. Okay, kernel subsystems can access each other. And again, when you study Linux, Linux is a monolithic kernel, and it's very common that you see this part of Linux, this part of the Linux kernel talks to this other part of the Linux kernel. It just accesses stuff directly because it's all monolithic. It's all part of the same large thing. Okay? The reason why people do it is because it's amazingly fast. Okay, remember the things that are slow. Context switches are slow. Trapping into the kernel is not the fastest. We like to avoid doing it if we possibly can. So those operations are slow. If I have everything in kernel mode, and it's in kernel space, and I need to access this part of the system, just access it directly. So it's super fast. And this is the reason why monolithic kernels are still so popular. In fact, we'll talk about it next week, but there was a certain version of Windows where Microsoft tried to move to a more microkernel-based architecture, where you actually have very small kernel and a lot of stuff living in user space. It was too slow. And so they started moving stuff back into the kernel so that now it has a monolithic kernel as well. Same thing with the operating system that Mac OS X is based on. It's, probably you've heard of Mach if you've dug into Mac OS at all. And the Mach kernel started out as being a microkernel architecture as well. And it ended up being monolithic as well because it was just too slow. Okay? So that's the reason why people use monolithic kernels so much. Okay, so monolithic operating systems still bug-prone, still have a lot of concerns about the stability and reliability of monolithic operating systems. So basically, one of the approaches that was explored was called a layered structure. And this was actually devised and pursued by Edgar Dijkstra. So he actually spent some time exploring this. And basically, each layer is separate from the layers below it. Okay, so it only talks to the layer below it, immediately below it, and it exposes some operations to the layer above it. So the layer is basically an encapsulation within the operating system. And so the higher layer really only talks to the layer immediately below it. Unless, of course, you have something where you need to go a couple of layers down, and in that case you might do that, but it tends to be infrequent. Okay? And like I say, it really only cares about the abstractions, not the implementation details. And the idea is you start building at the bottom, and when you start building the next layer, you test the crap out of the layer below it. And it allows you to create a whole bunch of tests, and so that you can sort of verify that these layers work well as you build up the structure. And so there's an OS called the OS, and so how do you refer to it? Well, it's the OS. And this was actually an operating system. It stands for, I can't even pronounce that, Technische Hogeschool Eindhoven. I actually know somebody who could pronounce that, but I didn't bother to ask them before doing this. But it's basically the Eindhoven University of Technology or something like that. That's basically what it means. So it's the Eindhoven equivalent to Caltech. And basically it was a batch processing system. So it was running on mainframes. So it was actually pretty simple back then. And they had 6 layers. And each layer only interacted with the layer below it. And so Dijkstra actually started at layer 0 because he's a computer scientist. And layer 1 would interact with layer 0, layer 2 would interact with layer 1, layer 0 interacted with hardware, and so forth. Okay? And each layer was tested. So when you're testing layer I, well, you have to have started building layer I plus 1, or else you can't have code to test layer I. So you just sort of are slowly building up the layers. And it's funny because you have to remember, this was on a batch processing system that they were running it. So you have your stack of punch cards or you have your tape, and you have to study the code because it may be a while before you actually find out if your thing worked properly. So they spent a lot of time thinking about what tests they needed to execute. They thought a lot about the test code, the code that was being tested. They thought about all these things. So it was a very methodical process, much more methodical than we have now, where it's just like, oh, I'll bang out a bunch of code, and then I'll bang out a bunch of tests, or maybe in the other direction, depending on your strategy, and then you run it, and it's like, okay, it didn't work. Well, I'll try it again, try it again, try it again. This was very, very methodical because of the context at the time. So layer 0, multi-programming, CPU scheduler. So now I have multiple tasks that I can execute. I have hardware synchronization mechanisms and so forth, or I should say hardware-based synchronization mechanisms, because it's actually possible to build synchronization entirely in software on your processor, which is kind of clever. We'll talk about some of those algorithms in a couple of weeks. But yeah, interrupt handling and so forth. Layer 1 was the virtual memory system and the pager, which is obviously an important part of virtual memory. Layer 2, OS communication to the console. Layer 3 is device I/O, including buffering. So layer 2 didn't really have any buffering. Layer 3 does. And then layer 4 is user programs, which was easy because the THE operating system didn't have a lot of applications to implement. It only had 5. I need to be able to build software, I need to be able to run software, and I need to be able to print. So not very complicated. They didn't have like, I don't know, a media player or anything like that. And then layer 5 was the operator or users. And Dijkstra famously says in his description, not implemented by us. So I guess he's begging off the testing aspect of the operator. But you can see how each layer just interacts with the previous layers, and you can test it very easily. What they ended up with was an operating system that was incredibly reliable and very few bugs, and the bugs that they ran into were really easy to figure out and solve, which is really nice. You'd think, okay, well, that suggests a good approach to operating system implementation. But what they found is that it took a long time to get to the final OS. And really what it was is they spent a lot of upfront time designing, and then implementation was very slow and very methodical, but they ended up with something really high quality. Okay? And so it's one of those things where it's a risk that companies frequently aren't willing to take. Like I say, why don't we use this? Well, oftentimes, it's especially with managers that aren't very experienced with software engineering, they see design as not work and implementation as work. Oh, you're coding? Good, we're making our progress toward the goal. Well, that may in fact be you're making progress, but maybe away from the goal. So, it's kind of a sad thing that companies don't take advantage of this more. One issue, though, is that layered approaches, you have things implemented as APIs and calls between APIs, even if it's all within the kernel, so you're not trapping into the kernel or anything like that. You still have calls that you're making. Well, that takes up time. Okay? And so you may have multiple call sequences that you have to go through to perform simple operations, and so that would slow down the operating system performance. Okay, so you can always make fewer layers that are fatter, and then the fatter layer is probably going to be harder to test and harder to debug, but it'll be faster. You can see how there's this trade-off between performance and reliability, which is kind of disturbing. We'll see it even more next lecture when we start talking about microkernels. Okay? Any questions about layered structures? Okay, the last thing that I want to talk about today is modular kernels. Because again, if you're familiar with Linux, you've probably heard that the Linux kernel is a modular kernel. It's a monolithic kernel. What does that mean? Which one is it? Well, it turns out that it's actually both. Okay? So monolithic kernels can definitely have extensibility issues because the kernel is all your operating system code that talks to peripherals, talks to itself, and then provides system calls to the application. So we'd like to support a lot of different devices. And like I say, if you wanted to add a new device to a monolithic operating system, what you would do is you'd write the device driver, and then you'd compile it into the monolithic kernel, so now it's in the kernel, and then you go ahead and load it and run your kernel. You have a couple of issues from this. One is that the kernel becomes ginormous because you have to have compiled in support for a lot of different devices, especially in the Intel PC world where you can plug whatever hardware you want into your computer, and then ideally the kernel will already have support for it. Okay? So, and like I say, more code means more bugs, which makes the kernel less reliable. So that's not good. Just to sort of mention a few things about this. See, back when I was an undergrad, and you would get Linux on a stack of 3.5-inch floppies about this tall if you wanted a complete distribution. Maybe you were lucky and it would only be about this tall if you just wanted the limited parts of the operating system. And then, you want to install Linux, you would be the operator slapping 3.5-inch disks into the computer as it's loading up all of the stuff. It was a different world, and typically the kernels started out having everything compiled in because we didn't have this loadable kernel module thing really very popular or very widespread. And so one of the steps that most advanced Linux users would go through is you start up a particular, I don't even remember the commands off the top of my head. I wish I could. It's like all of the stuff I used to have to do. But you'd start up the Linux kernel configurator, and you'd figure out which modules you wanted to include or exclude, and then you would rebuild the kernel, and then you'd reinstall the kernel, and then you'd restart your computer and hope it came back, because if it didn't, you were really in trouble. Get the stack of 3.5s again. And so that's how you would actually set up your computer, because you would want to compile out the stuff you didn't need so your kernel wasn't gimongous. Okay? We don't do that anymore. We don't have to do that anymore because we now have loadable kernel modules. Okay? And so if you have loadable kernel modules, you say that your kernel is modular. It's still monolithic, but it's now a lot more, it's a lot simpler to incorporate or to exclude different pieces of the kernel. Okay, so like I say, there's certain core services that are always compiled in, but there's also interfaces defined internally. So it does facilitate internal structure to have a modular kernel. So if you have things like block devices that I might want to support, storage devices, different networking devices, different other peripherals, then I have basically interfaces inside the kernel that can be specified, and then drivers can go ahead and implement those things. Now I have a new module. Well, how do I get that into the kernel? Who here has done like insmod and lsmod and okay, you guys are gonna have to at the end of this class, all of you had better have tried these things seriously. It's like basic. Well, it's not basic. It's more intermediate, but it's really cool and important stuff. Basically, there's a module loader that knows how to link modules into your kernel. And what it does is it actually statically links that module code into the kernel. So the module lists symbols, the module lists symbols that it needs, the kernel has symbols that are exposed, and so that thing is actually linked into the kernel. Which, I mean, it's crazy. You have a file of module code, and it's being linked into kernel space so that it can now access the rest of the kernel. You better trust your module. Okay? And like I say here, there's various facilities for unloading them and so forth. I think I talk about this in a lecture toward the end of the class. Okay. So basically, you get the same high performance of monolithic kernels. Modules can encapsulate some of their state by controlling what symbols they actually expose. And you can end up with a monolithic kernel that's a lot smaller because you only load the parts of it that you need. And operating systems are pretty clever. They know how to dynamically load modules based on what is necessary. Again, when you boot Linux, you notice some of those things. Okay, I'm probing for devices. Oh, you've got this device. Okay, I'm going to load this module that knows how to talk to that device. It just does all of it automatically for you. We had to do that manually back when I was an undergrad. Now, the drawback is you really only slightly reduce reliability because you still have these kernel modules that can talk to any part of the kernel. Like I can have a printer driver that messes with the process scheduler. That seems bad. But so you can still have modules that can bring down the entire operating system. So it's pretty bad. And so like I said, the modules basically reference and expose symbols that are global within the kernel. So basically, you have a slight improvement in the structuring of the operating system kernel, but not a huge improvement. And you have a slight improvement in reliability, but not a huge improvement. And so modular kernels, very valuable, very important, very common now. But really, they don't get a lot of improvement over, sort of basic pure monolithic kernels. Okay, any questions about that? Okay, so we've talked about basically all the ugly things. So yeah, this is basically a few details. Oh yeah, so monolithic kernel, just as one last little note, monolithic just means how much code is running in kernel mode. And in a monolithic kernel, you're running a lot of stuff in kernel mode that doesn't strictly need to be there. Okay? And that will be important when we start talking about microkernels. Okay, so next time we'll go ahead and continue this discussion of OS design patterns and wrap that up next time. We'll get back into the operating system design patterns discussion, which we had started last time. And remember, we covered several different approaches that were kind of unappealing. So we had simple structure, which is basically to say no structure. And MS-DOS is a great example of that. There's interesting details in the background of MS-DOS as well. If you're curious, you can go look at the history of that. We could have all ended up using another operating system called CP/M for PCs, but there were various issues there, and Bill Gates was able to capitalize on that opportunity and create MS-DOS, and now the world is the way that we know it. Layered structure, which is the THE OS, is a good example of that one. Monolithic kernels, where you look at initial versions of Unix and Linux, and modular kernels, which, again, modular kernels are monolithic, but they just allow you to dynamically load and unload portions of the kernel into memory. So they get statically linked into the kernel at runtime, and they can access anything in the kernel. The kernel can access them if they know about them. So you can't really say it's not monolithic. So modular kernels are just sort of a subset of monolithic kernels. We also talked about the separation between policy and mechanism and how important that is, because mechanism is probably not going to change very much, and it's usually grungy and low level, and you want to encapsulate it. You'll see that pretty significantly as you go through the course. But policy is something that you might want to change a lot, and it tends to be a higher level consideration. It tends to be something where changing policy can have profound impacts on performance or other aspects of the system behavior, but the mechanism is just sort of a grungy detail of how you do things. So a lot of people looking at operating systems asked a really good question, which is, what facilities do we actually have to put into the kernel? Do we have to put everything that's in a monolithic kernel in the kernel? There's a lot of stuff that you could look at and say, well, actually, no, I don't really need to put that into the kernel. So what kind of facilities would need this? Well, you think about, okay, process isolation. Clearly, I need some way of isolating processes. So that has to run in kernel mode. Context switches clearly have to run in kernel mode. Maybe a few other things that have to be in kernel mode. But if you think about it, very little actually has to be in kernel mode. So you look at these kinds of things, managing the virtual memory system or the interrupt controller, clearly setting up interrupts, being able to receive interrupts. The system call layer really should be in the kernel somehow so that I can protect applications from the kernel and vice versa. So another approach is called the microkernel approach, which is to basically put as little in the kernel as possible. Everything that doesn't need to be in the kernel is taken out of it, and it lives in a user mode application, if you will. It's a system application, but it's still outside of the kernel. It's running in user space, in user mode. Okay? And so like I say, most of the operating system is actually provided as user mode processes. So what facilities should be included in the kernel? Well, there was this guy, which we'll be talking about quite a bit today, Jochen Liedtke, and he had this minimality principle, which is stated here, and it's not complete, but it's stated here, and it's a pretty good guide. So a concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting competing implementations, would prevent the implementation of the system's required functionality. So things like virtual memory paging. Who gets to choose what page should be evicted? Well, that's something where having competing implementations makes a lot of sense, because sometimes under this kind of workload, I might want one kind of virtual memory pager. Under a different workload, I might want a different pager. So that makes a lot of sense to move outside of the kernel. Should I be allowed to have multiple competing implementations of context switches? That makes no sense at all. There should really only be one way of doing a context switch in the system. So that should be inside the kernel. So you can see that this was sort of his guiding principle when he was trying to think about how microkernels should be constructed. Now there's obviously another aspect of this which is not stated, which is that some things have to be inside the kernel because they can only be implemented in kernel mode. So that's another thing that should be part of the kernel, is if it can only be implemented in kernel mode. He doesn't really talk about that, but it is a critical aspect of what should be inside of the microkernel. So that sort of drives what is in microkernel. So these are the kind of things you typically see in microkernels. Process abstraction, so how do I do context switches? How do I actually manage CPU scheduling? So there's some details of that that will be in the microkernel. Interrupt handling has to be in the microkernel because the interrupt handler has to typically run at in kernel mode so that it can access the hardware. Interrupts need to be acknowledged, all of those kinds of things. Memory abstraction, so being able to do address space isolation needs to be inside the kernel. The memory separation between the kernel and user applications has to be controlled by the kernel and so forth. And then you have this other broad category of things, inter-process communication, which I abbreviate throughout this lecture as IPC. And typically you hear people call it IPC if they have been programming a lot, systems programming a lot. So inter-process communication facilities. If you have all these user mode applications implementing parts of your operating system, they have to talk. So you have some kind of IPC mechanism that allows user applications to communicate, and that's facilitated by the kernel as well. So you see basically three things that ends up being in microkernels. And so they end up being really small. Who here has heard of Minix? Anybody heard of Minix? A few of you have heard of Minix. Minix is a very well-known microkernel implementation of Unix. It was developed by Andy Tannenbaum. You, again, may or may not be familiar with the sort of very hot but now cool but still ongoing feud between Andy Tannenbaum and Linus Torvalds. Because Linus said, well, you really need to develop a monolithic kernel if it's going to be a usable system. And Andy Tannenbaum was very strident that saying, you have to do it as a microkernel. There's no way you can have a stable, running, mature system if it's going to be a monolithic kernel. And of course, now history has borne out that you can definitely create very stable and reliable systems on top of monolithic kernels. And there's a few other things that have come out of the dispute over time as well that we'll actually talk about as we get into the issues with microkernels. But Minix is an example microkernel. It's 6,000 lines of code in its kernel implementation. That's really neat. I mean, you can actually, a single person could write that, and a single person could maintain that. The Linux kernel is humongous in comparison. It is huge compared to the size of a microkernel. Okay? Now, obviously, microkernels depend on a lot of other facilities that are written in user space applications, but so all told, the operating system might still be about as large, but we're talking about what actually lives in the kernel itself. Okay, so other facilities provided user mode programs, device drivers. Yay, we can have really buggy device drivers and they won't bring down our entire system. File systems can be implemented as user mode programs, virtual memory pagers. And when I say virtual memory pagers, what I mean is it gets to figure out what page gets evicted, it gets to figure out what page is loaded, blah, blah, blah. It's not actually managing page tables or page directories. What happens is the microkernel calls out to the pager to say, what should I do? And the pager says, well, this is what you should do. And the pager tells the microkernel, and the microkernel carries it out. So same thing with file systems. It's not like the disk controller necessarily is managed entirely by the file system code in user space, but the microkernel will defer to the file system program to figure out how to interpret the data that it's seeing and so forth. So you could really say that microkernels are on one end of the spectrum as far as separating policy and mechanism. We separate it as much as possible. We get as much out of the kernel as we possibly can. Okay, so anything that implements a system policy should be a user mode process because we want to allow multiple completing implementations. So following this minimality principle. Drivers are unusual because they do need to talk to computer hardware. So typically, microkernels have to provide some way of allocating I/O ports and so forth to processes that need to use them. Because remember, the operating system kernel is still responsible for sharing the computer system resources between multiple applications in a way that's secure and fair and all of those kinds of things. So microkernel has to solve these kinds of problems. Also, you could argue that process scheduling should be outside of the kernel. The only problem is we are talking about a system that is trying to, remember, context switches are expensive. We lose about 20,000 instructions when we do a context switch. And that's a chunk of instructions. I'd like to be able to not lose that if possible. And so basically, a lot of microkernels already sort of betray the fundamental issue with microkernels by moving process scheduling inside the kernel so that we don't actually have to context switch to user mode program and then back to the kernel just to make that decision of who should run next. So that every time you wanted to switch from process A to process B, you do a context switch into the kernel and then out of the kernel to invoke the scheduler and then back into the kernel and then back out to the next process. That would suck. So typically, it's all kept in kernel just for the performance aspect of it. Okay, so we want to use a text editor to create and save a file. The text editor is a user mode process. It's running on top of facilities provided by the microkernel. So it wants to create a file. Somebody hits Control S for the first time, or Meta X, Meta S, or whatever. It's been years since I've used Emacs. I started accidentally from time to time. But anyway, so you have to save a new file. So there's a few other user mode processes that provide these facilities. So you have a file system process and a driver process for the hard disk. And the text editor says to the file process, I need to create a file. So what it does is it actually sends an inter-process communication message, or an IPC message we say, to the file system service saying, here's the file name, here's where I'd like to be on the file system. Would you please create this file for me? So drip through the microkernel. Then the file system service says, well, yes, I'd be happy to do that, but I need to get the disk to actually have its state change, so I'll talk to the disk driver. And so it sends another IPC message to the hard disk driver to actually perform that operation. And of course, what happens is this has to occur in reverse as well. The text editor is not really able to do anything until it hears back from the file system process. And the file system process needs to wait for the hard disk to do its thing. So you have an IPC message that goes back from the driver to the file system process, and then that goes back to the text editor process. Okay? So you can see how, wow, okay, so an operation that normally in a monolithic kernel would be a pretty fast thing. Now we actually have 1, 2, 3, 4 IPC messages that are sent and received to actually perform this operation. Okay? Wow, that you can probably see immediately what the problem will be with microkernels. So we communicate by message passing, like I say, an asynchronous one-way mechanism. This was sort of the way it was initially envisioned, even though here we clearly have a synchronous operation being performed. I want to create a file and save the contents to disk. So that is a synchronous operation. I really shouldn't go on until I've completed that operation. But message passing, as it was originally constructed, was an asynchronous mechanism. So I send a message to another process, and if I need to find out what happened, then I sit and wait for them to send a message back to me. Okay? But this has to be done through the kernel. So the process A invokes the kernel to send the message, and then process B asks the kernel for the message, are there any messages for me? Because the file system is clearly going to be servicing a lot of other processes. So typically, this would be implemented as a set of queues. Each process would have its own queue, and when you send the process a message, it goes into that process's queue for that process to pick up the message later. And so you see you have some copying that can go on. So again, we have another issue that we sort of can run into with this approach. So the text editor sends the little create me a file message, and that gets copied into the queue for the file system. Well, that's in the kernel. And then when the file system process says, where's my messages? Then the kernel has to copy the message out of the kernel memory back into the file system process. So we have a couple of copies going on. That also is slow. We would like to not do that. Now there's various other abstractions that are typically provided as well. Am I allowed to send messages to a given process? Am I allowed to send any messages at all? So the file system process clearly would say anybody can send a message to me. But you might have other processes where they're like, I really only want to receive messages from so-and-so. So again, processes get to control the kinds of things that they allow. Now, this copying issue. How might we solve this copying issue? Anybody have any ideas how we might solve this copying issue? We have all the tools to know how to make this at least a little tiny bit better just from the things that we talked about in the last half of CS124. How could we use virtual memory paging to solve this? Yeah, we could have a situation where, as an example, this is a great idea. So the text editor copies its message into the microkernel, and instead of the file system process receiving a copy from the kernel could just map that page into the file system process. So now the file system process magically sees it appear, but now we've cut it down to one copy. That's one option. There's various constraints that you could have. If we allow a sending process to write to the message that it has just sent without affecting the receiver, what the receiver sees, then we have an interesting constraint, an issue that we have to solve. So that's kind of what makes these systems hard. You basically always end up having to perform about one copy at a minimum when you pass a message to another process. Okay? There's some ways of even working around that, but it tends to be that you have a minimum of one copy that you perform when you pass messages. Okay. All right, any other questions, comments about this? So it's an interesting approach. You can see that the benefit is pretty obvious. So there's actually a couple of benefits, which I really only talk about this one, is that it is an astonishingly reliable system. The other aspect of it that's a big benefit is that you are forced to design everything modularly, and any effort you spend up front trying to design systems well is a huge boon. It's a huge benefit to spend time up front designing. So this encourages that as well. If a system service crashes, this is what's so cool about it. Just restart it. The whole system is fine. It's like, oh, my file system crashed. That's lame, but I'll just restart it. So that's nice. The printer driver crashed. I mean, the reason why I keep mentioning printer drivers is because printer drivers were like one of the things that would always cause Windows to crash before it actually got preemption and blah, blah, blah. So, buggy printer drivers from some third party, and it's got a bug in it, and the system just falls over because of it. So if you have a system service that crashes on a microkernel architecture, fine, just restart it. Now, of course, just because you can restart a service does not mean that you don't end up having sadness. Because, you may have that the file system still gets corrupted if the file system is not implemented very effectively. Okay? Or like I say here, you have a network service, and it has connections to some remote clients, and the network service falls over. Well, you still will drop those connections, or you'll still drop state that was being communicated. So you still have situations like that need to be designed around carefully. It's not like it's just a perfect world without any more thought. So the solution is the same as it's always been. And if you want a really good book about this kind of thing, then I would get Jim Gray's transaction processing. I'll put that on the CS124 bookshelf so that you can track it down if you want. But Jim Gray had a, a really astonishing, brilliant insight, which is that software fails and hardware fails. So why don't we design systems so that they can be transacted? And you know, transactions are not just a database thing. In his world, everything was transacted so that anything could fail and it wasn't a fatal situation. Okay? But like I say here, this is not included in a microkernel. This might be a service, or it might be an aspect of a service to make sure that it's more resilient to these kinds of situations, which do inevitably occur. Okay? So that's a benefit. Another benefit, let me see. Yeah, so this is wild. I have this inter-process communication facility, and processes communicate with each other to provide services for the operating system. There's no reason why I can't put them on multiple cores now. They just talk. Or I have multiple servers in a rack, and they talk. So you can actually have one operating system running across N computers with different services provided on different machines, and they all just do their inter-process communication over a network. That's pretty powerful. And you can even implement that non-local IPC facility with user mode services, because now you have network IPC. Well, that sounds like a really great user space application you could provide. It knows how to talk to the network. It knows how to receive messages that are then forwarded onto another process on another machine. So you can see that this approach is very extensible to multiple machines. If I want to start running a system on multiple machines or multiple cores, it's very easy to do that. And like I say here, this made microkernels extremely interesting. In fact, again, has anybody heard of GNU Hurd? H-U-R-D. A few of you have. So that is a multi-computer, multi-server, microkernel architecture. It's designed to be able to run on multiple machines as a single computer, which is really interesting. You know, and I suppose that as networks get faster and faster, we'll be able to implement this kind of thing relatively easy. Of course, the major drawback, which should be obvious at this point, is the performance issue. That you have this problem that all of this communication and all of this message passing and the attendant context switches, the attendant kernel traps to receive messages or send messages, it becomes really expensive. So like I say, your message passing is asynchronous. So the text editor has to trap into the kernel. And then it gets blocked, so we have a context switch away from it to something else. And so it stores, like it says here, the microkernel stores the message in the file system queue. The file system also has to trap into the kernel to receive its message. So one message pass, two kernel traps, and one context switch at least. Probably more. Most of the time we have interactions between applications and services, or services and other services, is synchronous. Why are we trying to use an asynchronous model to solve a problem that is usually synchronous? Like I say, process A can't progress until process B responds. Nonetheless, process A sends message, process B receives message. That's two kernel traps. Process B sends message, process A receives message. Two more kernel traps. It just adds up. It's kind of ridiculous. So, and then of course you have all the copying issues that also occur here. Now, we're going to talk about a specific example, which is one of the most widely discussed examples. It's CMU MOOC. MOOC actually started out being called MUC, but there was an Italian graduate student on the team who could not pronounce MUC accurately, so he kept calling it MOOC, and which is a pretty Italian thing to do. And the guy running the project loved the name, so he went ahead and decided to call it MOOC. So it's not that it's blazingly fast; it's kind of the opposite. So, but anyway, it was a CMU project from 85 through 94. Very sort of impactful project. I've mentioned it before. OS 10 runs on a MOOC kernel, or a variant of a MOOC kernel. So, you know, it lives on. It's very, very widely spread at this point. So it was implemented on top of BSD Unix. It had a great approach to the problem. We'll start out adding IPC extensions, so inter-process communication extensions, to the BSD kernel, so that we can actually continue booting this operating system and using it. Great idea. After it was finished, then they started migrating facilities out of the kernel and out into user space. And so finally at Mach 3, that's when they finally had a microkernel architecture. And of course, this was exciting because of all the reasons I talked about before. You know, hey, you can run this on a multi-computer system. Because if you think about it, what had occurred up to that point was you had mainframes, you had mini computers, they all ran monolithic kernels. But they were still a single core. So it was like, okay, I can understand what's going on, even though the system is monolithic. People were starting to create multi-core systems and multi-processor systems. And suddenly, taking this giant code base and migrating it into a multi-processor, truly parallel implementation, it's like, wow, that's really difficult. And it is really difficult. And so they thought, well, if we could just go ahead and build a microkernel architecture and approach the operating system development that way, maybe we can migrate to multi-core systems really easily. And so that's why Mach was like super exciting to people. But its performance was awful. So just a little bit of discussion. I don't want to get too much into this because I don't want to lose too much time. But Mach had ports. Those were basically where messages could be sent to. And so these were set up on behalf of processes in the kernel. You would have basically ports set up, and you could specify permissions, who could receive messages, who could send messages, and so forth. And they basically, you could think of them as structs. And there was some fields that were always there, and then you'd have some sort of payload that would be delivered. So you'd say, where is it going? Where to send a message back to if there's supposed to be a response, and so forth. So you basically had all of this information that could be passed. And there was one API call that would basically send messages and receive messages. If the port queue was full that you were trying to send to, well, you were blocked because there's no room for that message to be stored into its queue. Okay? So you had this one function that was used for all of these kinds of things. And this was the constraint that I was talking about. When I send a pointer, basically, to another process, what am I allowed to do to the memory that that pointer points to after the call comes back? Am I allowed to write to it? Do I have to wait until I get an acknowledgement? So this was one of the concerns that they had to solve. So like it says here, Mach tries to avoid copying message data too many times. But if I'm going to send a message and then be allowed to write to that memory after I've sent it, but before the receiver has received it, then I need to come up with some way of protecting the message itself. And so in Mach 2.5, basically, like I say here, message virtual pages were mapped into kernel space. They would be copy on write. So if the sender tries to write to a page after it was queued up to be sent, then it would just do the copy on write trick. It would make a copy of the original, and then the sender could transparently write to its message data without actually affecting the receiver. Okay? So basically you can see here you end up with 0 to 1 copies on the sending side. I get a copy if I try to modify the data, but if I don't try to modify the data, I get no copies. When the message is received, that virtual page is mapped into the receiver's address space. So that's kind of nifty. If the sender didn't modify it and the receiver receives it, then you basically have 0 copies. That's pretty slick. If the sender decides to modify it, well, then I have 1 copy. Because the kernel duplicates the page, and then the page is mapped into the receiver's address space. So that's Mach 2.5. Mach 3 kind of simplified this a little bit. Basically, like I say here, duplicating the sender's message data into the kernel. So Mach 3 went ahead and just made a copy. So maybe I'd have to go back and look at the reasons why they abandoned the Mach 2.5 approach, because it seems better, but it's clearly more complicated. So maybe they had bug issues. Yes? That's exactly correct. Yeah. So the abstraction that the Mach message API presents is that the sender creates a message in its own process address space, and then it calls Mach message and hands over a pointer to it, and then the kernel does magic. And as far as the sender knows, it can carry on doing whatever it wants. that message is somehow moved, as if by magic, into the receiver's address space. Yeah, the sender doesn't care about any of this page management stuff at all. No, the kernel basically manages this all transparently. So the sender, like I said, the sender just has the abstraction that it can send a message. It may write to the memory. It may not. If it later tried to access that memory and the kernel had already migrated the page to the receiver, then the kernel could transparently create a new page there or duplicate the old page there. So basically the kernel is responsible for maintaining an abstraction that the sender is just sending a message. And the message is somehow, as if by magic, duplicated into the receiver. The kernel's responsible for managing all the actual implementation details of that. Okay.
You might be asking, like, what happens if there's a memory issue?
If there's a memory, well, I'd have to understand what memory issue in the kernel, because if, for example, the receiver's queue is full, yeah, if the receiver's queue is full, then the sender's blocked. So the sender's not actually allowed to proceed. So, like, who is running out of memory in this situation? The whole system. Well, then you have other issues. Yeah. I mean, you have to remember that with all these system calls, and you should be learning this actually on the first assignment, with all these system calls, the system can always say, I can't do it. I don't have enough resources. So you try to create too many processes, the system can say, I can't create any more processes. The system's allowed to do this. So it might be that in that specific situation, Mock would just say, I can't deliver the message. Try again later. And it could certainly do something like that. Obviously, there's a lot of vagaries and nuances to all of this that one could explore. But the main issue here is we're trying to reduce the amount of copying because this is inherently a slow mechanism. It's kind of a really slow mechanism if you look at it. Okay, so another issue, we'll try to speed up here, is that Mach3 uncovered another issue with microkernels, which is that these components that are managing things don't always have all the information they need to actually solve the problems they're responsible for solving. So the virtual memory pager is a really good example of this, where it's required to make a decision about what page should be evicted across all the processes in the system. But the issue is it doesn't know how other parts of the kernel or other parts of the system actually behave. And so what they found is that Mock did, funny that we're talking about low memory situations, Mock did terribly in low memory situations because it wasn't aware of all the other parts of the system that may have, may be applying memory pressure. It may not know what things have constraints or demands. So again, you could probably design around this issue where the pager starts getting really sophisticated, but then when you have enough information you have to share with the pager, well, then passing those messages is going to become really slow. Monolithic architectures really don't have this problem because all the subsystems can see each other. And subsystems can interact directly with other subsystems very efficiently, so you kind of avoid this kind of issue. So this was one of the big issues that they uncovered with Mach 3.0. Mach 4 tried to fix some of these things. You'll notice the last point here. How did people try to solve the performance issues they ran into on Mach 4? By undoing the microkernelness of the microkernel. We're going to start moving stuff back into the kernel. So we're taking a step back to, sort of the monolithic world. So that's when Jochen Liedtke came into the picture, and it was kind of a really interesting thing. I wish that he'd lived longer. But you kind of unfortunately find that a number of these people that were really impactful on computer science, some of these systems implementation things, typically died, unfortunately, well before their time. He died in a car accident, and I just wish that he had lived longer because we would probably see some really powerful things. But he started looking into microkernels. It became very interesting to him. And he looked at this stuff and he said, part of the problem is just that these microkernels are being designed badly. And so he started designing his own microkernels, which you can see how he named them. L2, L3, L4. He just sort of called them lead keys system 2, system 3, and system 4, and so forth. And basically re-implemented the IPC mechanisms from the ground up, and he had them humming along. Order of magnitude performance improvement. First thing he said, if most of our interactions are synchronous, why actually try to implement them on top of an asynchronous mechanism? Let's provide a specialized synchronous send and then receive operation and actually incorporate that into our process scheduling details and so forth. And so now I trap into the kernel to send, but I also inform the kernel I expect a message back. So I don't need to trap in again to receive. I just trap in once and then I wait. Okay, so now you've already cut that overhead in half. L4 again tries to eliminate a copy during message-based IPC when it has to copy stuff at all. We'll talk about that in a second. So process A invokes the kernel to pass a message to process B. The kernel temporarily maps process B's target memory into process A's address space. So instead of copying it into a kernel queue and then into process B, why not just manage the queue in process B's address space? It's a little bit riskier. You'll notice that this approach to microkernels is a little bit riskier because now process B could really mess up its queue. But if we do this, then we eliminate a copy in the kernel. We can just copy it directly to process B. Also, numerous messages turned out to be really short. If I want to say, yes, the hard disk access succeeded, yes, I created the file for you, why actually copy memory? Why not just pass that stuff in registers? That makes a whole lot more sense. And so short messages are handled differently in the L4 microkernel as opposed to long messages. L4 also schedules a little bit more fast and loose than Mock did, for example, where basically if I have a situation that I do a send and then receive to another process, I am basically telegraphing that I am incapable of proceeding until process B executes. And if I do that and I have like a huge percentage of my time slice left or something like that, why even invoke the scheduler? I know another process that can proceed. Why don't I just switch to it? So in these situations, the scheduler, I shouldn't say the scheduler, I would say the kernel, because it doesn't invoke the scheduler, switches directly to process B and allows it to start executing. Okay? So that removes a huge amount of the overhead. And so there's a number of research papers about this. If you're interested in looking at some of those things and seeing the performance improvement that was able to be achieved over things like Mock with lead keys, various approaches, it's really remarkable to read about. And it really sort of revamped interest in microkernels. Like I say here, it does affect real-time scheduling. I'm not going to talk about that just for the sake of time, but you can imagine if you're going to stop invoking the scheduler may say, yeah, but so-and-so really needs to run right now, and you're like, I don't care, I'm just going to switch to this other process. Then clearly you start having real-time scheduling guarantees start to be affected. Okay, so this was good for microkernels. It really increased interest in them, but they do reduce reliability to some extent. You can see how we start relaxing the constraints and the boundaries between processes and the boundaries between process data and kernel data for the process. We start introducing a little bit of risks. So there are actually variants of the L4 microkernel approach that are being used in a number of places. So mobile devices, hypervisors are starting to rely on the L4 kernel. You can go look at the Open Kernel Labs website if you want to read more about L4. And they have a surprisingly impressive list of customers that they are working with. And then you also have the open source L4 kernel if you want to go and start working on that, or look at how they do things if you want to emulate it yourself. I think this is very promising, and I think we have not seen the end of it. So it's kind of exciting to see the microkernels live on with some of the obvious brain damage resolved so that we can actually make them suck a lot less. Okay, any questions? So that's microkernels. Of course, these have performance issues, mainly because of all the IPC overhead that's required. And so hybrid kernels are sort of like microkernels, except that we migrate stuff back into the kernel. Okay, so it's kind of like a blending between microkernels and monolithic kernels. You have a lot more structure in place, because remember, if you try to design things with a microkernel architecture, you are required to think about the interfaces between systems. You can't just throw it all together and patch things wherever you want. So I just want to talk about a few of these things kind of quickly. OS 10 you would call a hybrid kernel because it is based on Mach 3, but a lot of services have been migrated back into the kernel to make it fast. So OS 10's kernel would be an example of a hybrid kernel. Windows NT, which probably nobody uses anymore because we're sort of on to Windows 7 and 8, and there's been a lot of development on those. That would also be a good example of a hybrid kernel. When they started designing NT for the first time, they said, well, Mach is really promising. This was back in the 90s, and so we're going to try to emulate Mach's microkernel architecture. They did it, and it was too slow. Well, how do we solve that? We'll start migrating stuff back into the kernel. And there's a few others as well. The reason, you probably never heard of Chorus OS, but there's a number of research operating systems which are definitely worth checking out if you're curious about this kind of thing. Chorus is really interesting because it basically allowed you to create a microkernel architecture, a microkernel operating system, and then what you could do is declare that certain user space services would be sucked back into the kernel. So they call that co-locating it with the kernel. So we're going to move this thing back out of user space, back into the kernel, and now we're going to actually run it as part of the kernel. So you could, the modularity of this was configurable, so that you could actually do this. It is a pretty powerful and interesting approach. So Chorus is definitely one to consider if you're curious about that kind of approach. The last major approach that we're going to talk about today, this basically covers all of the approaches, by the way, which is kind of neat. But, so we say that there's a major difference between monolithic kernels and microkernels. Throw everything in the kitchen sink into the kernel versus pull everything out of the kernel that we possibly can. But it's interesting because that's really only one dimension. They still have a strong similarity in that they both provide this really simple abstraction over the computer hardware. They don't actually allow applications to interact with the hardware directly, like nearly at all. And the file system is a great example of this. We've been talking about it a lot because it's useful for the command shell. But, applications don't care about the file system format or anything like that, or even what type of device. They just interact through this very simple Unix API with the file data. So exokernels are another approach that basically goes in the exact opposite direction away from that. Exokernels explore the question, what if the OS didn't force us into a specific abstraction for interacting with the hardware? Which is kind of an interesting question to ask. This concept was also developed in the mid-90s by the MIT Parallel and Distributed Operating Systems group. And they sort of asked the question, well, who really knows how we need to use the hardware? The answer is the application knows what it's doing and what it wants to do, so why not let the application manage the hardware directly and get the operating system out of the way? Now you might be saying, wow, that seems like a really horrible idea, and certain aspects of it would definitely be a horrible idea. Basically, the OS still retains the power of deciding who gets access to what hardware. So the OS still guards applications from each other, keeping applications from stomping on each other. You can have this part of the disk. I don't care what you do with it. Do whatever you want. You get this other part of the disk. You're not allowed to trample on each other. So things like that might be the way that applications are allowed to access hardware resources in a safe way. Applications can say, I want these ports. I want to interact with these ports. Get out of my way. I want this memory region. Stay out of my way. And then the OS would enforce that. The exokernel, again, the fact that we're giving direct hardware access is, again, orthogonal to whether it's monolithic or a microkernel. Although you can imagine that since exokernels are moving out a lot of things like device drivers and stuff like that, because we're going to let the application do it, they tend to be more in the microkernel vein anyway, because they just don't need to provide very much. But the whole concept of an exokernel is just that I don't control the hardware as much. The application does much more. So how do we actually provide hardware abstractions? They tend to be provided in this approach called a library OS, or a library operating system, which runs on top of the exokernel, but it knows how to talk to hardware. Now the device access is actually in user space. Okay? And so that sits on top of the hardware, and it allows you to have standard APIs provided in a simple way. And then applications can just decide what libOS they want to use. So they don't have to use every library OS. They're not constrained to. If they want to talk directly to hardware, they can. If they want to provide their own libOS, they can. And if they want to use some other libOS that's provided by the system, they can. So they have a lot of flexibility. So MIT, exploring this whole exokernel approach, created XOS, okay, for exokernel operating system. And of course, they created a confusingly named libOS called XOS also on top of XOS. And basically, that provides the standard Unix APIs on top of, in a libOS that applications can choose to use or choose not to use. So that basically, again, allowed them to start running existing applications like Emacs and GCC and other simple applications that are written against the Unix API. So those things could continue to run on top of XOS. But then applications could also ignore that libOS if they wanted to. And so they created this web server called Cheetah, named, because cheetahs are fast. Not because it sounds like cheater. And basically, it had a whole bunch of customized things that it did. Okay, so think about what a web server needs to do. And I need to be able to serve web pages, but web pages access other shared resources. So why don't I create a file system that clumps those things together on the disk so that I don't have to slew the disk head very much? Great idea. I mean, this was fantastic for the 90s. Now we just throw a solid state drive in there, spend a little bit more money, and the problem goes away. But that was the approach back then. They had a custom TCP IP implementation that understood that HTTP was what was being used on top of it, so that they could actually optimize some of the the flows through the protocol. And then when you have TCP retransmits, which you invariably do, well, don't actually use a network buffer where you have to copy data off the disk into the file system cache and then into the network buffer and then out across the network. Why not collapse those buffers? So now TCP retransmits come directly out of the file system cache. That's fast. So they were able to get, again, nearly an order of magnitude improvement over comparable web servers at the time because they were getting so much of the overhead out of the way, which is pretty clever. Okay. Any questions? So that's the idea behind exokernels. What happened to the web server? You could probably still track it down if you looked carefully, but it probably is like boring and slow now because there's been so many, there's some interesting things that we won't talk about for a few more lectures, but things like, I don't know if you've heard of ePoll or Select, but you have various abstractions that are provided on the hardware. I guess what I'm trying to say here is the hardware is making such fast strides and improvements in capabilities. Now we have solid-state drives. We don't care about disk seeks. We don't care where files are. And memory's getting faster, and networking is getting faster, even management of the networking resources and so forth. So that now we can actually, we're getting to the point where we can create modern web servers using more standard approaches that are not nearly as scary as Cheetah would be to manage and maintain, the source code of, and you get really good performance out of it. So it's like these kinds of approaches, while interesting, have kind of remained only in the experimental phase. So you haven't really seen them catch on. But yeah, if you want to look up Cheetah itself, I think you could probably still find it. I don't know that MIT is doing any research right now. What you'll notice a lot of times is that schools will do research in areas because it's interesting to some of the professors or some of the graduate students, and then over time, areas wax and wane. They come and go because people, there's not people interested in studying a particular topic at a particular school. So I don't know the current status of it, but I imagine that it's probably defunct by now. Okay, any other questions? I could be totally wrong about that, of course. So yeah, still open area of research. So you can, I have lots of links in this lecture so that you can go look at stuff. So the Parallel and Distributed Operating Systems Research Lab, you can still look at that. A few other exokernels which you might want to be aware of. Nemesis is a now defunct operating system. And basically, it was an effort to try to migrate as much work out of the kernel for multimedia processing and multimedia management, move as much of that effort out of the kernel as possible. So they didn't set out to create an exokernel, but they just ended up creating one because that's what the problem sort of required. Okay? So that would be one to look at. You can see it's an old project that is not really developed anymore. But there's another exokernel, XOMB, which is, at least last time, 2 years ago, was still being very actively maintained. So again, if you want to look at an existing active exokernel project, you can look at XOMB. All right, so there's some ones for you to look at. So these are basically the full spectrum of approaches that people have tried with operating systems. You have the simple structure, which is no structure, layered structure, which is a very rigorous, you sort of have a subsumption architecture where each layer is covered up by the layers above it, and you have very simple APIs and very heavily tested. Monolithic kernels, which are very popular because of their performance. Microkernels, which are very popular because they are aesthetically beautiful, but not popular because they're not very fast. And then exokernels, which are out on the periphery. Not really very popular just because of how much effort they require. There are variants of these. You might get on the OS Dev Wiki, which is a great website for this class. I probably should collect some links to that kind of thing as well. You'll see nanokernels, picokernels, and it's like, really? They're just mixings of these. Okay? So you take exokernels and throw this away or add that, and you get some other kind of kernel. This basically covers all of the important details. Okay? There's also one thing that's obviously missing, which is hypervisors. Okay? I don't recall if I actually have a hypervisor lecture. I need to write one, but I'm not sure I have space for it. So when I say I didn't mention hypervisors yet, we may not get to them. I hope we do. I don't know. Maybe if we had a special lecture, then you might all come out for that. And because the classes end on a Wednesday, so maybe on a Friday we could do a special hypervisor lecture. Okay. Any questions? All right. So we'll pick it all up on Wednesday.